Welcome to okay, record. Okay.
I'm recording.
Recording. Okay. Good evening, everyone. Welcome to CCBS NeuroTalk Salon. I'm today's moderator. I'm Christy from University of Macau. I'm a PhD student at the Center for Cognitive and Brain Sciences in the Department of Psychology. NeuroTalk Salon is organized by the students of CCBS at the University of Macau, aiming at enhancing the academic sharing, networking, and development among CCBS and beyond. Today, we are so glad to hold the 10th Salon via a virtual form, and we are also pleased to have Mr. Li Yuhang to share his recent computational modeling work or working memory. We also have about 20 participants online. Before our talk, we would like to ask the participants to rename your alias by your real name plus your affiliation. For example, Christy, University of Macau. Thank you for coming and cooperation. Please also kindly note that a recorded version of this talk will also be available online soon after the event, maybe a few days later. Yeah.
Hopefully tonight.
Okay, tonight. Okay, next slide. First, I'd like to introduce today's presenter, Mr. Li Yuhang. Yuhang obtained his bachelor's degree from the Department of Psychology in East China Normal University. Currently, he is a PhD student in psychology at Professor Nie Qiyang's Computational Psychophysiology Lab at the Center for Cognitive and Brain Sciences and the Faculty of Social Sciences in the University of Macau. Yuhang uses the computational modeling method to investigate the cognitive mechanism underlying a variety of working memory and some decision-making tasks. Okay, now, Yuhang, you can share the screen and start now.
Okay, thanks. Let me share my screen. Okay, this one. Oh, okay, this one. Can you see my screen?
Yeah, perfect.
Yes.
Okay. Okay, first, thanks for the detailed introductions from Christy. I'm very glad to be here to introduce some of my recent work to all of you guys. Very welcome very much for all your attendance. So as you can see, we are very junior researchers. I just got my bachelor's degree, so I might not be as experienced as you. So if you have any questions or comments for today's presentations, you are welcome to interrupt at any time and we can discuss about that. So, okay, I will start to introduce the topic. The topic of today's presentation is going to be evidence for trunking of global and local representations in working memory. Most of you here may be familiar with trunking and working memory because it's all famous conceptions in cognitive psychology. But for the global and local representations, I think I may need more explanations here. Okay, here is an example of a hierarchical items with global and local features. As you can see, it is a man. And if you look closer, you will find this man is actually consists of many fruits and vegetables, something like this. So the shape of the man is called the global representations, and the detailed fruits and flowers, something like this, are called the local representations. So as you can imagine, in our daily lives, this kind of hierarchical objects are all around us. We can find everything with their global representations and their shape, their sizes, and they also have detailed texture as local representations. So the major question we want to ask today is how people remember global and local representation in their working memory. Do local and global representations will be included independently or jointly? To investigate that, we design a novel stimulus with hierarchical representations in continuous feature space. And the major result find that we find an influence of global-local difference on the working memory performance. And we perform a factorial model comparison procedure to explain what kind of influence could be. The best model is the trunking models. So then we ask, why subject do trunking? So we do that by proposing a rational resource trunking model. So we will talk about that later. So let me first introduce some previous studies. Researchers focus on this kind of hierarchical features from last century. It's a long time ago. The major focus on the global precedence effect. That's so-called the global features are always processed with higher priority, like the large EU, in contrast with the small issues, will also always be processed first. And also in the working memory test, the global features always will be encoded better than the local features. But here the global precedence effect is not what we mainly focus on this study. So to investigate how people encode global and local representations in a continuous feature space, we designed the stimulus like shown on the left. The benefit using this kind of stimuli is that we can manipulate the difference between local and global orientations. As you can see here, the global orientation is indicated by the direction of this shape. And the local features is indicated by the texture, the direction of texture. Okay, so we can answer what the working memory performance would be if the local and global difference is 20 degree or 6 degree, something like this. We cannot do that with this kind of discrete object space. So here is our task. First, in each trial, we expose subject with 3 or 1 stimulus. Then after a brief delay, we ask what the direction would be in either of these locations. If the cued color is green, subject will indicate the global directions. If it's blue, subject will need to indicate the local features. So the global trial and local trial are mixed across different trials. So for one trial, subjects need to remember both global and local features in their working memory. Both of them are task relevant. So here is the result. We can see that there is a significant success effect in their arrow distribution. And then there is also a rather significant global precedency effect, but this is not what interesting. What we find interesting is that along with the increase of global local difference, the working memory arrow increase at first, then keep still. This trend is most obvious in the local ZZ3 conditions, as you can see here. In other 3 different conditions, it also a small this kind of trend like this. So it can be saying that global local difference has a major effect on the working memory performance. So in next experiment, we use the same task procedure, but in one specific block, we only queued global or local features in that. So in one trial, subject will only have to remember one of local or global orientations in their working memory. Only one of them is task relevant. So here's the results. Same thing finding the global success effect and global precedence. But what interesting is when we investigate the effect of global local difference, we find also a significant trend in the local success-free condition. That saying that it means that even if global feature is task irrelevant, it still be able to influence the response in the local queued trials. As the global local difference goes larger, the working memory precision goes worse. The error goes larger. So here is all our basic behavioral results so far. Any questions? So if no questions, I will explain how we explain this kind of global local effect. We give out 3 hypotheses for this kind of global local effect. But before I introduce those hypotheses, let me first introduce what the default situation would be. That's the situation when both global and local features are encoded independently. In that condition, the response will join from a von Mises distributions. You can regard von Mises distribution as Gaussian distributions on the circular space. So the mean value of this Gaussian distribution will be the stimulus value. And the y-ness is controlled by a free parameters kappa, but different with the Gaussian distribution. The kappa increase, the kappa decrease with the y-ness goes larger. That means if we get large kappa, that means the distribution is normal. So kappa basically means the working memory precision. Here is the first hypothesis, bias. Bias means in a specific trial, subject's response will shift towards the other task irrelevant features. Like in the local probe trial, the response distributions will be shift towards the global features. And the extent of shift is controlled by a parameter bias and the global local difference. So we can imagine the larger the global local difference, the larger the error will be. It is same as what we found in the results. So here we use 2 parameters, bias local and bias global, to model this effect, because we think the bias for local and global trials might be different because we find the global dominance effect. Okay, here's the first hypothesis. Here's the second. Second is swapping. Swapping is also a famous working memory concept. It's saying that in some trial, the subject will get confused which features, which target, or which item to respond. Like in a local probe trial, subject will sometimes report the global value. That's called swapping. We use a parameter swapping rate to control the ratio of this kind of swapping trial. Okay, that's how we implement swapping. And the last one is trunking. Trunking means if for a trial, if the global local difference is lower than a trunking criteria, this trunking criteria is also a free parameter. Then we assume this subject will do trunking. Do trunking means the subject will encode both global and local value as one item. So the response distribution will centralize on the mean value of global local features like this, and the y-ness will be smaller. So that means the working memory precision will become higher. That's because originally subjects need to encode 2 items in their working memory. But if they do trunking, they only need to encode 1 of them. So yes, they get more space to encode the item value. So the precision will become larger. But if the global local difference is larger than this parameter, then the response distribution will be the same as the independent state region. Okay, these are the 3 hypotheses we proposed. So to test which of these 3 hypotheses is true, or some of them are true, another are not, we do a factorial model comparison procedures. As you can see here, we treat every hypothesis as a factor which can be turned on and off in a model. And you can see here, we also add another additional factor, variable imprecisions. We do that because we want to keep in consistence with previous working memory model research. So variability in precision means that the y-ness of response distributions is not consistent across the whole task. It can be vary from trial to trial. So for a trial, the distribution the response y-ness can be drawn from gamma distributions. And there is additional parameter controlling the shape of this gamma distribution. So in summary, we've got 4 factors here. We use factor here because we assume all of them can be effective in one model. So in the most complicated model we construct, we implement all of the 4 factors in it. But in the most simple, in the simplest one, we'll implement none of them. So as you can see here, we used 4 common parameters for all the models. These are different kappas for different conditions, different global local and ZS1 and ZS3. We use different kappa. And if a factor is on, we add additional parameters to the model. Like if we implement the variability imprecision in model 1, we add another tool to the model. And if we implement bias, we add 2 bias to the model. And here we used 2 trunking criteria for factor 4 trunking. Each one is for 1 set size, because we assume the trunking criteria for ZS1 and ZS3 could be different. So eventually, we get 16 models, which 2 times 2 times 2 times 2 is 16 models. Then we compare the goodness of fit for them. Before I show you the results, any questions you want to ask? Okay, if no questions, I will continue. Here we evaluate the goodness of fit using AIC value. You can regard this as the smaller the AIC value, the better the goodness of fitting will be. So as you can see here, the bars are the difference between models and the best model. So the best model here is this one, which is variable precisions, no bias, no sloping, but trunking. This is the best model. And we can see that all the models which implement variable precision and trunking have low AIC value. It means that the fitness of this model are good. So in the later factor effect analysis, we also find the trunk factor and the variable precision factor is significant better. It has significant larger effects than those other two factors. So log likelihood difference here is the log likelihood difference between the model which implement this factor and the models which didn't implement this factor. So, and then comes to the experiment 2, the block 1 design task. We found the exact same results at experiment 1. So also trunking and variable precision are the most important factor in the model. But it is kind of tricky because in experiment 2, task one of the features is task irrelevant. Subjects only need to remember local or global features in their memory. But in that case, the model comparison indicates subjects will also do trunking. That's kind of strange, but it might be some evidence for the implicit trunking effect, some kind of like that. And this is the predictions of our best model, the model with variable precision and trunking criteria. This one is for experiment 1, this one is for experiment 2. And you can see the line are the model predictions, and the dots are the real data. And the red one are success3 conditions, and black one are success1 conditions. So as you can see here, the model predictions is quite good. So it captures the main trend in the data. But for the model with variable precision, bias, and spot swap, but no trunking, the prediction is not that good. We will find the trend finding in the data was not captured by the model prediction. So we can see that the trunking factor is really important for the model. Then we to be consistent with previous experiment, previous research, we do another change detection task with mixed-wide design. Similarly to previous task, subject need to remember 3 or 1 items in their working memory. Then another stimulus was exposed to subject. Subjects have to tell whether this new item was the same as the previous item showing in the same place. So the change can happen in the global level or the group level. In the global level or local level, okay. That's a change detection task. So we find the same effect of local trunking, but here is a little difference. We found some not that good fitness for this kind of model, but it's mainly because the ESA difference among all models are not that large. You can see that not larger than 10. Is not a very large ESA difference. And about the predictions, we can see that also the best model captures the main trend in the data. It is the global local effect here. But in the model with precision bias and swap, the model did not capture the trend very well. But in summaries, the global local effect observed in the change detection task is not that obvious. I think it's mainly because change detection task is not a very sensitive measurement of working memory precisions. So we better take the results from the delay estimation task. So as far, we got the data from 3 experiments, and all the factorial model comparison results are consistent the model with variable precision and trunking can best explain the data. So here comes the next question: why subject will trunk? To answer this question, we might want to review the concept of trunking. Trunking means subject will encode several or two items in their working memory as one item, because those items features are close to each other. Subject do that to save some cognitive resource or to remember more item in the working memory. So you can regard trunk as a rational strategy for subject to get a better performance. So we get the idea of rational resource working memory from a previously published research called the rational resource visual working memory model. We use that model to explain the trunking phenomenon we observed in our data. So at first, let me first introduce what is the rational resource working memory model. So its basic idea is that subject will find the most economical working memory precisions if they are going to encode one item in their working memory. So what is the most economical working memory precisions? It's saying that when people encode one item, they will pre-calculate the cost of encode that item, and then they will choose the working memory precision which makes the cost the lowest. Then they take that precision to encode that item. So the total cost is actually consists of two parts. The first is the behavioral cost, which means the goodness of they have a good memory of this item or bad memory, and the neural cost, which indicates the mental effort subject would put on that item. So in the original paper, the author assumed a linear relationship between working memory precision and the neural cost. You can see they capture the trend by a free parameter lambda. And by behavior cost, it just calculates the expect mean error with given a specific working memory precisions. So you can see that it actually decrease with the behavioral cost will decrease with the working memory precisions, and the speed of decreasing will increase along with the working memory precisions. You may find the equations rather complicated here because we implement the variable precision function equations here, and we use another logout function to evaluate the mean error. To understand this logout function, you can imagine when a subject are going to estimate their behavioral cost, they will compare two error, like 10-degree error and 20-degree error. Regard of 10 and 20, they might think, oh, this 200% difference. So it's a large difference. But regard 70 and 80 degrees error, they might think, oh, that's not a very large difference. So you will see that the subjective sensitivity of behavioral cost will actually decrease with the error increase. This is kind of complicated, but never mind, it's not a major concept. So we kind of implement logout function here. So in summary, we get the total cost as shown in this curve. The total cost will first decrease and then increase along with the working memory precision goes larger. So we can easily get the working memory precision, which makes the total cost the lowest here. So now we get the working memory precision subject will use for a specific trial. But the remaining question is, what the situation would be if subject to trunking. So if subject to trunking, their neural cost actually will be the half of original neural cost. You can look at this, the middle bottom plot. It is because that originally they have to encode both global and local features in their working memory. But now if do trunking, they only have to encode one of them. So the neural cost will be half our original neural cost. Okay, but regardless of behavioral cost, because if subject to trunking, their response distribution will shift to the mean value of local and global value. So the actually the behavioral cost will go larger, as you can see in the left bottom plot here. The trunking conditions behavioral cost is larger than non-trunking condition. So in summary, we can calculate the total cost for trunking and non-trunking condition. And how we decide whether subject will do trunking or not do trunking for a specific trial. We can just compare the total cost of trunking and non-trunking conditions. As we can see here in this plot, the trunking condition gets the lowest total cost for trunking condition is lower than the lowest total cost for the non-trunking condition. So in that case, subject will do trunking. But if the non-trunking conditions has the lowest total cost, then subject will not do trunking. So that's how we decide if subject do trunk or not do trunk. So after we decide that, we can generate the response the same way as we implement in the factorial model comparison procedures. We just join the response from a Vomin's distributions to get the prediction. Okay, it is how the rational resource trunking model works. So any questions so far? Okay, if no questions, I will continue. Here's the model comparison between rational resource model and other models we tried. We will find, unfortunately, we didn't get the best fit compared with former models. That's why we only fit the rational resource model for experiment 1. Okay, but this is not a very large difference compared with those worst model. It's okay, but the difference between rational resource model and the other best models are also significant. It is also significant. We cannot ignore. But regard of the prediction, the things is that we barely can tell the difference between the prediction of rational resource trunking and the best model we get from the factor model comparison procedure. So we can see that the difference for these two plots is very little. So fairly speaking, rational resource trunking did capture some pattern in the data, but maybe because we still cannot capture some noise or other features in the data, maybe the size effect of other things. The rational resource trunking model cannot beat the best model we found. So all the results and methods we've used are present. Here's the summary part. First, we found that along with the increasement of global local difference, the memory error will first increase and then stay still, especially when the working memory load is large. And these findings are in sharp contrast with the with the object integration count of visual memory representations. And from the factorial model comparison procedure, which shows that the best model are the models which implement trunking and variable precisions rather than the models implement swapping or bias. So we can see that trunking is better explanation than swapping or bias for our data. And in the end, we proposed the rational resource model. And it indicates that the trunking might be a rational resource strategy to minimize the summary of behavior cost and neural cost. We said might be because we didn't get the best fit for in that model. So that's all can we say, unfortunately. So this is all my presentations, and thanks for listening. If you have any questions or comments, we can discuss about that. Thanks. Okay.
Thank you for impressive talk, Yuhan. Okay, now the floor is open for the audience. Please feel free to ask your questions. If you have any questions, please unmute yourself. You can ask questions. Also, you can set your questions to the chat box. Any questions?
Hello, can you hear me?
Yes.
Yes.
Yeah. I'm very nice presentation and the research. And yeah, my question is, how did you use the GG or anything else to get the response, to get the response of stimulates?
To get a response, you mean the predictions?
Yeah.
We didn't get response from the prediction. We fit the model to the data. So technically speaking, we calculate the prediction, calculate the distributions of response for every trial, and then we calculate the log likelihood for every subject.
Oh. Yeah.
Then we select then we select the best parameters. So if you do you actually asking what kind of model fitting method I've used?
So you just use the reaction, the behavior data. You do not use any. Oh yeah. Perfect. I see. Yeah, and
okay.
yeah, but in this case, how did you? Could you please move the slider a little bit previous to the previous one? I remember that there was a curve.
This one?
Yeah.
Okay.
Yeah. The chunking, maybe more. 24.
This one?
24. This is 23. Yeah, this one. Yeah, this one. Here, how did you get this curve? You just use a function to write to.
You mean in the slide? I just draw this by hand, but in the model, we have MATLAB package which can draw value from the Vomises distributions or calculate the probability density from Vomises distributions. So basically, we can calculate that.
I see. And the last question, you might say it, but I might miss about the Vomises. misses this function.
Okay.
The definition of this function.
Okay. Maybe I should explain more about that. You can regard this as a normal distribution on circular space. So because we use directions as our fit stimulus, so we use momentous distributions. You can regard this as a normal distribution.
Beta.
This one?
Oh, yeah.
Beta.
I see.
Okay, beta is the parameter we use to describe the influence of our arrow, of the arrow. So here we calculate the behavioral cost by this. And this part is what the arrow will be. And this part is the population, is the probability of observing that arrow. And this parameter is used to let me think how do you describe that? It's used to describe the degree, to describe the relationship of arrow and the influence of arrow. Can you imagine that? Because in psychology, in psychology, the psychology effect is not linearly. So the relationship of arrow and the effect of arrow is not linearly. So we use an additional parameter to model this trend. And why we use that? Because the original paper published here, this one, use that. So we also use that.
Oh, wait a moment, please wait a moment. I would like to remember this paper. Sorry, could you please move the paper, the name of the paper?
Okay, I'll share this in the group later.
Yeah.
Okay.
Yes, thank you. And maybe I can ask some suggestions from you.
Okay, sure.
My project, I don't in my project the stimulus is not a kind of structured data, and I need to. So if I want to move this kind of study to the unstructured data such as language, or for example a verb. For example, in the how could I do to make it structured?
Is that a memory task?
Yeah.
If that's a memory task, you may need a continuous feature space like direction, like color, something like that. If you use verbal stimulus, I'm afraid that's not supported by this model, unfortunately.
Oh yeah.
Okay.
Yeah, I see. Thank you.
So okay, let me see if there are some questions.
There is a question
Checkboard.
in chat box. Yeah.
Xie Hanbo from Peking University said that for your model comparison, it seems your models have very few differences in ESC. Did you conduct a Bayesian model selection? I will show you the result. I will transform to the result part. Okay. I don't know what standard did you use, but for our research, I think a difference about 20 here and 10 is not a very small differences for this. Do you agree, Hanbo? Okay, I will continue to answer your question if you are not convenient to respond. Did you conduct a Bayesian model selections? That's a good question because we we were planning to do that, but we kind of failed because it takes too much time to run the model, run the code. And also, I think we kind of have too much models. We have 16, so that might not be a very effective procedure we can use. So that's my answers. And if you have more questions, please ask in the chat board. And then, okay. Then question from Tan Jingbing, your rational resource model show that in some circumstances, trunking is better than non-trunking. How to make sure that this situation in your experiment is on that range? I think I didn't explain very clear on that page. You mean, I assume you mean in this trunking is better than non-trunking. You mean this one? This one, okay. It is not speaking that in some circumstances, trunking is better than non-trunking. It is, so in this page, what we should do is to estimate the vocabulary precisions, which makes the total cost the lowest. To do that, we calculate the total cost separately for trunking and non-trunking conditions. So we first assume this trail subject to trunking, then we calculate the total cost. And okay, you have to leave. Okay, thanks. And again, we calculate the total cost for the non-trunking. If for the non-trunking condition, assume. Then we compare the lowest total cost. We calculate for that. Then we decide whether subject will do trunking or not do trunking. So that's how we get predictions of subject's trunking behavior. Is that clear? So it is in this part is not the result, it's our method. Okay. Is that enough to answer your question? Okay.
I saw Jeremy is also here. Maybe he is an expert in the resource rational analysis. Maybe you can discuss with him, right?
Zhemi, are you convenient for speaking to give some comments on this presentation?
Hi, thank you for the talk. So yes, I heard of this project a long time ago. Not long time ago. It's from your advisors, and I didn't realize that the difference in AIC is in this case. But I mean, I don't see very worry about this AIC because usually.
You mean this?
Yes. Yeah. Usually the resource rationale model have this kind of problem in AIC, BIC. One of the reasons is the resource rationale problem usually combine two models. One is the original model, and the other is the resource model. And this increase the parameters, but usually it would have better log likelihood here. The reason why you have the worse AIC here is maybe it's because the experiment paradigm is too simple. You only have two trunking and you only have two stimuli. And perhaps if you increase the experiment complexity, the advantage of the resource rationale model will be better than the non-trunking model. And you can see the difference. So this is the only thought in my mind I have right now. And I don't have any comment on the other part.
Okay, thank you very much. Actually, yes. to answer, not because I think rational resource trunking model is can answer another whole question besides this experiment. So to construct a model like rational resource trunking model, we might need to conduct a separate experiment. So instead of just counting the old data with this new model, that's kind of reasonable explanations. Thanks for your advice. And okay. Strategy work. Tan Jingbing says, you mean that the memory strategy will shift between trunking and non-trunking based on the value of G? I'm not saying that. Okay, maybe I'm terrible in English and didn't explain that very well. I will explain that again. Okay. The trunking and non-trunking strategy, whether we use trunking and non-trunking strategy, is determined by the lowest total cost represented here. As you can see, there's the red line here is the lowest total cost for the non-trunking conditions, and here is for the trunking conditions. We compare these two values and determine whether we used trunking and or non-trunking strategy instead, and then we decide the value of G. Okay, we compare the total cost, then we decide trunking when or non-trunking when, then we decide which J we will use. That's the procedure. Okay.
Anyone have some questions? Okay, I think even though I haven't understand all your presentation, especially some advanced formulas, but I really love your hypothesis and the comparisons between models. I think through this way, we get a robust and persuasive results and conclusion. Okay, now is the end of this.
I saw there's one more like question or comment from the chat box, like JB Gore.
JB Gore.
That's what I want to say. You mean
that's what I want to say.
Okay.
You mean that's the question you want to ask, or that's you agree with my explanation?
So, Mr. Gore, you want to unmute yourself and speak up?
Hi.
No response.
Okay.
And never mind, Christy, maybe we can wrap up if there's no more questions.
Okay. Oh, yeah, that's okay.
Okay.
So,
if there any questions?
No more questions. No more questions. Okay,
okay,
that's all.
Okay, if there are no further questions, let's call it a day. I want to thank Yuheng and all the online participants. Thank you for your attention and participation and making the event happen. We would also like to express our special thanks to the Office of CCBS. Thank you for your support. And we also want to thank Brain Technology. Thank you for your help in propagation. And you can subscribe our WeChat account to follow the latest information. Okay, at last, we would like also audience to open up the camera and take a group photo. Okay. How
Okay.
we can make a group photo?
Christy, you quit the screen sharing first, and I will take a group photo from my side. Stop the screen sharing. Okay. Okay.
Stop sharing.
Yeah.
Hello, Professor Nia.
Hi.
Hello, everyone. Some more faces.
Hello. Well, let's welcome my
Oh, I saw
my classmate Li Wanru. My
Yeah.
classmate Li Wanru from Peking University.
Hello.
My dear classmate
So me.
in my
It is NU.
yeah in ESNU. And thanks for the means attendance.
Yeah,
Zhoming is my group mate from the CP Hack competition. He is very impressive researcher from my point of view.
Wow.
Yeah.
Okay, look at the camera, guys. 1, 2, 3, smile.
Okay.
1, 2, 3, smile. Okay, Christy.
Okay. Thank you so much. And